Okay, we are still in homogeneous differential equations from the second order. Today we will talk about the Euler Cauchy equations. Firstly, let's take the general form of an Euler equation. It should be looking like x squared y double prime plus a x y prime plus by equal 0. So we have constants a and b that we want to look for when we are trying to solve, or when we have an example that we want to solve. So on the side in here, basically the Euler Cauchy equations are depending on representing the complex form of this equation in a more simpler to handle form. So basically what they do, they replace the y with x to the power m, and the y prime, basically the derivative of this equation, which is m x to the power of m minus 1, and it represents the y double prime to be equal to m multiplied by m minus 1 multiplied by x to the power of m minus 2. Okay, if we substitute all these values back in the general form of the Euler's equation, we get second general form for that equation. So the main equation should look like this: m squared plus m multiplied by the constant a minus 1 plus the constant b equal to 0. Now we need to focus a little bit on this form. So when we have an equation or a problem that is identified as an Euler Cauchy equation, which looks like this, then when we move it to the next form right here, now what we're gonna do, we want to solve this quadruple equation. When you solve it, you have different cases. Either the values of m are real numbers, or the values of m are equal, which is repeated roots, or you have complex roots. So let's talk today about case number 1. In this case, let's say m1 and m2 are real numbers. Let's say m1 is 4, m2 is 6, m1 is minus 1, m2 is 7, etc. If that's the case, then the general form of the solution would be y equal c1 x to the power of m1 plus c2 multiplied by x to the power of m2. Now let's take an example for a problem that applies to case 1. So having an example in here, let's say we have x squared multiplied by y double prime plus 2x multiplied by y prime minus 6y equals 0. Now we're trying to apply what we learned in the methodology we discussed moments ago. So first, we change this equation into the simpler form, which I call it the M form. So you will have m squared plus m multiplied by a minus 1. Let's change the color here. So this is A and this is B, based on the discussion that we had before. So now we have m squared, so using this m squared plus m multiplied by a minus 1, which is 2 minus 1 plus b, which is plus the minus 6, gives you minus 6, all equal to 0. And we can simplify this form to be m squared plus m multiplied by 1, of course, minus 6 equals 0. Now, finding the roots of this equation will give you m1 to be equal to plus 2 and m2 equals to minus 3. Okay, now again, using the general form, since we have m1 and m2 now, we can say the final solution should look like this: y equals c1 multiplied by x to the power m1, which is 2 in this case, plus c2 multiplied by x to the power of m2, which is minus 3 in this case. And this is the final solution that we have been looking for from the start.